let's talk about Green's theorem. Very good. We have some nice tools like Green's theorem and more that help us to compute line integrals. Green's theorem. So this guy says, suppose you have a curve like C, which is positively oriented, which is moving counterclockwise. Let's see, be a positively oriented and piecewise smooth simple closed curve. Okay, simple, it's closed curve. Suppose D is the region bounded by this curve C. These are the information that we have so far. Then, if your vector function is represented by P and Q, and these scalar components of your function are continuous, first derivatives with continuous first derivative components, then the line integral of P dx plus Q dy over curve C is equal to the double integral. So you can convert your line integral to double integral of partial derivative of Q with respect to X minus partial derivative of P with respect to Y over region D dA. So Green's theorem says if these conditions are met, then you can convert your line integral into a double integral. So here you have a positively oriented curve like C. Positively oriented, it means that you have counterclockwise. Orientation. And here you have the region D, which is the region bounded by this closed, simple, smooth curve. Very good. Give us an example. Sure, let's go over one example to feel more comfortable about what's going on here and how to apply the Green's theorem. Question says, evaluate the line integral of x to the fourth dx plus xy dy over curve C. And this curve is defined as follows. C is the triangular curve consists of line segments starting from 0, 0 to 1 and 0, and then from 1 and 0 going to 0, 1, and from 0, 1 to 0, 0. Okay. Let's see what we have here and how to apply Green's theorem. Let's graph the base. But the very first step is graphing the base. What's the base look like? Okay, so I have my x-axis, I have my y-axis, and then I have, starting from the origin, 0, 0, 2, 1, and 0. So in this direction, this is the very first line segment that you have. Then from 1 to 0, 1, 0 to 0 and 1, which goes this way. And then it goes back to the origin. So this is my triangular region, and here I have my V, which is the region bounded by C. So this is C, moving counterclockwise, positively oriented, and as you can see, it is closed. So using Green's theorem, by Green's theorem, this line integral over C, x to the fourth, dx plus xy dy can be converted into the double integral over region D. So note that the very first component is your P and the second component is your Q. So you have the partial derivative of Q, which is xy, with respect to x, minus the partial derivative of x to the fourth with respect to y, dA. Very good. So this double integral becomes the double integral partial derivative with respect to x gives you y, partial derivative with respect to y is just 0, dA. Very good. So take a look at this. Here you can say that, hey, our x is bounded between 0 and 1, our y is bounded between 0 to the top, which is the line y equals to 1 minus x. So x is bounded between 0 to 1, and y is bounded between 0 to 1 minus x. Okay, so this guy becomes the integral 0 to 1, 0 to 1 minus x, y, dy, and then dx. Going straight here. So here you have 0 to 1, a half y squared, 0 to 1 minus x dx. This guy is a half integral 0 to 1 and 1 minus x to the second power dx. Well, you can use u sub here and you get negative a half, a third, 1 minus x to the third, 0 to 1, or negative 1 over 6, 0 minus 1, or 1 over 6. So the line integral converted into double integral, and we calculated that